10.1 talks about 2x2 systems of equations. So real quick, some vocabulary here for us relating to the three different things that can happen when you're working with a system of equations. You can have two equations that cross each other. The point at which they cross each other, that's your solution. If it has a solution, your line is said to be, or your system of equations is said to be consistent. So if your lines are parallel, then your system of equations is inconsistent. Now, if your lines are one right on top of each other, then they intersect at multiple points, an infinite number of points, making it consistent. But it's not enough just to say that it's consistent. To distinguish it from this case, we call this one dependent, when the lines are really one on top of each other. They're the same line. So dependent. This would be independent because these are different lines, and these are different lines, so it's independent as well. Now, let's take a look at solving some of these things. So I went out online this morning and I picked up some data from the internet. Now, I kind of cherry-picked it a little bit, not trying to make any statements here, but just trying to show you that people can use this stuff. So I plotted accident rates on one axis, or with one equation, and murder rates with the other equation. Now, before I press this circle here and show the equation, can anyone tell me which of the three cases that I'm going to get? Am I going to get something consistent, inconsistent, or dependent? Well, let's see. Consistent would mean they cross each other. Inconsistent would mean they're parallel, and dependent means they're the same. So I think we can eliminate the one case. They're not dependent because these are different lines. They have different coefficients, etc. But of the other two, can you figure out which one I'm looking at? Is it consistent or inconsistent?
Consistent.
Has to be consistent. To be inconsistent, then these lines would have to be parallel. They'd have to have the same slope and the different intercepts. So here you go. And with this, we can find where these two lines intersect. The theoretical point at which the murder rate and the accident rates are the same would take place 19, almost 20 years after this data set started. Now, of course, this is cherry-picked. It's not really trying to make much of a statement or anything like that. Just showing you that you can use this stuff in applications. Now, that's not the only thing that can happen when you're trying to solve a 2x2 system of equations. That is, you get a nice solution. Let's take a look at some other things that can happen as well. So I'll give you kind of a nice little basic case. So x plus 2y equals 5 and x plus 2y equals 7. Now this might make you a little bit curious right at the start, because the left-hand side is equal in both cases, but the right-hand side is different. So how could this equal two of the different things? So, one of the ways to solve a system of equations is by the addition method. In this case, I'd multiply the top equation by -1 and simply get negative x minus 2y equals -5 and add it to the bottom equation. What do I get when I add it to the bottom equation? What pops out of this? Well, on the left-hand side, I get a 0, and on the right-hand side, I get a 2. But 0 doesn't equal 2. So that's false. And what that's telling me is that there's no solution. This is inconsistent. If this is inconsistent, what should I see when I graph these lines? Does anyone know?
Parallel.
Yeah, they don't touch. They're parallel. So let me shut these off. And if I graph these lines, exactly what we expected. They're parallel. They never touch. Now, the important thing to notice here is that when the variables dropped out, I got something that was false. That's kind of a little hint or clue that your system of equations has no solution. How about this next one here? Let me scroll down and we'll look at 10x plus 4y equals 14 and 15x plus 6y equals 21. So that's our system of equations here. I can shut off this one. Let's go back over here. Bless you. Now what I notice here looking at this one is that I can again solve this one by the addition method. If I wanted to cancel out the x's, if I multiply this top equation by negative 1.5, negative 1.5 times that's going to put a negative 15 right there. So negative 15x minus 6y equals negative 21. Add the 15x plus 6y equals 21. And I guess I kind of overachieved here, because when I add these together, what do I get? 0 equals 0. And I think you've seen me do things like this, perhaps on other videos or someplace else. But 0 equals 0, as silly as that is, that's true. And because it's true, it's telling us something different than what we learned up here. It's telling us that, oh, well, these lines are what? Dependent. So really, one of them is just a multiple of the other. If you take 1.5 times this one, you'll get this one. So it's the same line twice. Now, here's where this class is going to go a little bit beyond what we did with our last class. What you need to do is you need to take and solve this, because Desmos, excuse me, not Desmos, WebAssign is going to want your solution in the form of x and y. Except they don't want just a y. I mean, they would if these were numbers, but they're not. So let's take this and solve for y. 10x plus 4y equals 14. 4y equals negative 10x plus 14. Divide both sides by 4. And then politely put that in lowest terms. Negative 5 halves x plus 7 halves. Beautiful. So instead of writing it as an x and y like this, what I could write it as is x and then this expression right here, which is equal to my y, negative 5 halves x plus 7 halves. So that's my solution. This is a parametric solution, is what it's called. You put in a value for x, and then you use that expression to get your value for y, and these pairs of points trace out your solution. Let me pause here for a second. Are we okay with this example here? Okay, let me give you some visuals to kind of back that up here. So coming down here, there's my first equation, and here's my second equation. Notice that one is right on top of the other. The red equation and the blue equation, they land on top of each other. If I were to look at pairs of points in the form that I had outlined down here below, right here, I used an S as opposed to an X just because of the way Desmos works, but it's the same thing. If I change my values of S, notice that it always gives me points that are on this line. In fact, let's just make S a nice even 0, 0, and 3.5, or S equal to 1, etc. Each time I get points that are on this line. So this parametric form of the equation traces out this line. Nice, nice. Now, one last little thing to take care of here for systems of equations of this form. Sometimes you have equations like this one down below, and let me shut these off. So 0.2x minus 0.2y equals negative 3.4. And then the second one below that, negative 0.3x plus 0.5y equals 6.9. Now if it has fractions or if it has decimals, either way, it's not a bad idea to clean these things up first. So I can multiply the top equation by 10, and that'll give me 2x, should have been a decimal here, 2x minus 2y equals negative 34. And then I can multiply the bottom equation also by 10. Now if you had two decimal places, like 0.32 or 0.51, I'd multiply by 100. That will move the decimal 2 places to the right. Negative 3x plus 5y equals 69. Now in this case, there's probably a couple ways you could solve this one in terms of getting rid of one variable or another one. I'll leave it up to you here. Do you want to practice the addition method again, or do you want to do the substitution method? Probably wouldn't hurt to see a substitution problem. So what I'll do is I'll take this equation and I'm going to solve it for x. 2x equals 2y minus 34. Just moving this to the other side. And then I get x equals y minus 17. I'm going to plug that into this expression and then solve for y. So I'm going to plug in a y minus 17 from here and get negative 3y plus 51 plus 5y equals 69. Combining like terms, I get 2y equals 18, so y equals 9. Beautiful. If y is 9, I can plug that back in here. X is 9 minus 17 gives me negative 8. So x equals negative 8. That's the other part of my solution. If I were to graph this, what would I see?
Wait, where did the negative 8 come from again?
Plugging the y equals 9 into this expression for x.
Okay.
So I got 9 minus 17 gave me the negative 8. So my solution is negative 8 and 9. If I were to look back at my graph, then what will I see? Bless you. I should see that these two lines intersect each other exactly at that point. And they do. This is a nice way to double check yourself in terms of your work. Now, for those of you who think, oh, I'll just do everything on decimals, I'd be careful, because starting in the next section, you're going to need to do these things by hand, because we'll be working with 3x3 systems of equations. And unfortunately, to graph a 3x3 system of equations, you'd need 3 dimensions, and decimals only has 2. So it can't graph this stuff anymore. So you're kind of stuck. In any case, questions or follow-up on this? All right. Good luck. Reach out if you need some help.